And I checked the chat and we got 2 questions for Peter already. And the question is about the generalization, right? Every time we're discussing about AI, deep neural networks, reinforcement learning, how general is that approach really? Did you do some experiments? And I don't know, if we go now to an unknown racetrack, how good would your algorithm be?
Yeah, so in this experiment, we trained a specific policy for each car track combination. We have looked at generalizing across multiple cars on the same track or a single car across multiple tracks. We don't have results that we're publishing about that yet. What we found is we can still learn to be pretty good in most of those situations and generalize pretty well, but not at that superhuman performance level. That kind of takes this hyper focus on this one particular track and car combination, which is also true of humans, right? They're not, you can take Lewis Hamilton to another racetrack that he's never been on in a car he's never driven, and he's still going to be really good, but he's probably not going to be the world's best driver on that track with that car.
Thank you. If you have any questions, just go up there and ask. Now we have these amazing speakers here. It's your time to ask.
A question for Jonathan.
Mm-hmm. So we have one question for Jonathan, and I would just like to read that out loud so everybody can hear. So Jonathan, a coupled slip rear tire model was used in your latest demo. Compared to your previous paper, what are the insufficiency of saturated tire models?
Great, thanks for the question. Great to see you again, Tong, by the way. So awesome. So the sliding tire model that I used in the previous paper really only works when the tire is fully sliding. And the couple slip model, however, that we use is an isotropic slip model that also works when the tire is not sliding. So now the MPC controller is able to more fluidly transition between grip driving and slip driving, as opposed to needing to be drifting, because only when you're drifting is your model valid. So that's useful, not just for transitions and such, but also for returning to grip driving and the overall goal of driving in all situations. It's not the best tire model in the world. It certainly doesn't have enough parameters to fully capture both very low slip, as in like the handbrake model, the handbrake part of the section. And I think it could have more accuracy, I think, in the non-linear part, but not yet sliding part of the model for racing applications. But I think it's sort of the right direction to go. When I find the one true tire model, I'll let you know. But thank you.
All right, thank you very much. So we have the first question from our audience. Please go ahead.
Yeah, it's also a question for Jonathan, kind of related to that. So in some of the earlier slides describing the non-MPC based controller, it kind of implies that you want to formulate the dynamics of the controller in a regime that basically only applies for when you're drifting and slip. One of the things that you showed on the MPC controller was that it actually covers properly into under grip driving. So I'm kind of curious, is the MPC model truly general to cover both dynamic modes, or is there some pattern switching?
Yeah, we actually use the same model that we use for the drift controller for other controllers that are similar, but not drifting. So I think so I think basically the model is actually quite general. So it does work in both regions. Again, it's not perfect I think it's perfect in not okay. I think it's really good in the drift region. It could have some improvements in the grip driving region. I think that there are always things that you leave out in your model. And I think a lot more online adaptation and behavior adaptation would really help. But I think it works in 95% of the cases that we've been looking at, which is pretty cool. But thank you for your question.
All right, thank you very much for this question and coming up. And Nandan, he's from our lab. Thanks for being here. And yeah.
Of course. Thanks. The question for Peter. You mentioned that you trained versions of GT-SOPI for track car combinations. How many samples or how many hours of driving time do you need to be able to develop that superhuman performance?
It takes 20 PlayStations about a week and a half to 2 weeks to get to that superhuman performance.
And is that with 20 cars running on the same?
It's that whole mixture depending on the scenario. Different tracks have different mixtures of specialized scenarios and general scenarios. We've estimated it's somewhere in the 10 to 20,000 hours of driving practice to become as good as the best people in the world.
Thanks.
Thank you for your question. Yeah, like a human. So we have next speaker. Yeah.
I have also a question for Peter. When the material about Sophie came up online, some sim racers on YouTube did an analysis of how Sophie drove in some certain situation. In particular, I remember a turn where where Sophie with the SLS and tried to steer over a certain slip angle. So what I want to ask is that should we exploit the physics simulation limits or glitch in these systems, or should we try to constrain the model in order to give it more in a more realistic way?
Yeah, so that's a good question. There was one particular corner, that same one that I showed in Dragon Trail Seaside, where GT Sophie in the time trial version of the policy tended to like drift across the curb in a way that all the humans thought was not controllable. It appears to be controllable, at least within the game. I think so there's a couple ways to answer the question. One is, what GT Sophie learned to do was available to the humans. It may have had, prior disposition to do things that were more realistic and not explore those limits of what the game allowed. But all of those things were not penalized by the game engine. I think this tool could also be used to find out if your simulation has little loopholes that maybe you'd like to make more realistic, and could then tweak the boundary or examine how to make that a more realistic section of the track.
Hello, my question also goes to Peter.
Okay.
You mentioned that you had a population of agents. Did you identify any distinguished strategies that emerged? And did you observe some strategy cycle such that agent A wins against agent B consistently, and this agent B wins against C, but C also wins against A?
Yeah, the whole process was a little too computationally intensive already to like fully explore that space of comparative strategies. We tried, one of the things we found to be true between the July race and the October race, and you can see a lot of the details of this by watching the races which are all online, or we have some blog posts that come out that highlight some of these points. But we noticed in the July race, there was a moment where I think it was Yamanaka again came up behind one of the GT Sophie cars, and our car kind of moved out of the way and slowed down a tiny bit, lifted off the gas maybe, and allowed Yamanaka to pass. And when we investigated that, we saw that we just didn't have enough experience with a car coming up behind us in a slipstream scenario, because the prior agents we had trained with weren't good enough to do that. And so one of the things we had to do was up the love, train better agents and then use them to train an even better agent yet again.
So that's,
I would say we couldn't identify like special powers within each set, but making them good opponents was really important.
so you did some form of league-based.
We did a team-based 4 versus 4 policy versus policy analysis too.
Thank you.
Yeah, thanks.
So we have one question for Jonathan, and I reformulate that a little bit, because when you and I had our chat in California, you told me about that you watched and learned from the drifting racing, right? Mm-hmm. And watched the cars. So when you watch that, what you can learn from the drifting in the end, which in comparison to a normal race car? Is it like the yaw rate behavior? Is it the side slip, right? Mm-hmm. What do you think is the most thing you learned also from watching these racing series?
Yeah, that's a great question. Thank you. Thank you for asking it. I think the primary takeaway for me is that if you're going to drive a car up to limits of handling as you are doing in racing, you need to know what to do if you go past those limits, right? It's very easy to go past the limits you're trying to get to 100%, because you could misestimate a parameter slightly or have a slight sensor fault or whatever, and now you get 101%. The car is at 40 degrees side slip, hopefully your controller knows what to do at that point. So I think, a lot of what we do is sort of like contingency actions. So if you are in that scenario, you can't just wish yourself away from that scenario, but you need to be able to handle it. So if you spin a car, you do actually need to keep the throttle on, so you keep the weight on, and push the car, keep pushing the car around the corner and make sure it completes a turn. So I think that's a big part of it.
Mhm. Awesome.
I think we recently did some race car driver training just to like improve safety driver performance. And most curricula for race car driver training actually starts with learning how to deal with oversteer and understeer on a skid pad before you get anywhere close to the track. And I think that's important to remind that before you push your car to limits, you need to know what to do when you go past it. And that's, I think, a big motivation for us.
Mhm.
Thank you.
Yeah, thank you. We have still time for one or two questions, so go ahead.
I also have a question for Peter. So the training of Sophie involves some form of self-play, but the thing that surprised me was that form of self-play still had some human intervention in there. So you actually selected the policies that you wanted to train against. Was there a specific reason for that you didn't use standard self-play where you just compute ELO ratings or something like that? Or?
Yeah, so there's a couple of reasons. It's possible that kind of standard self-play will work in the future now that we know more about the domain and more about what it takes to make good agents. But up to this point, if we didn't inject our knowledge, and especially sometimes, one of the problems is that etiquette, there's no ground truth outside evaluation system that can tell us that was an acceptable behavior and that wasn't. So we have to go watch the races sometimes, and this sounded like a good policy, but we watched some races and we're like, that was, it was bumping cars left and right or driving them off the road in a way. And sometimes it will drive a car off the road but not make contact, so you won't get a signal that something bad happened, but the opponent just felt uneasy and kept going until it was off the road, and we had to filter out those behaviors by hand.
I see. Thank you.
Sure.
Maybe one short question and then we move on.
Sure. One for Evangelos on his learning parameters in NPC while deployed on a sort of real world platform. A couple questions there. One, what kind of parameters were you tuning? Traction parameters, and the second part of that is what kind of ground truth information and sensing information do you need about that outside platform to be able to do that?
Did you understood that? If not, he can come over here.
If you can repeat the question, that would be awesome.
Nanan, come over here. Yeah. 1 second.
Sure.
Yeah. So kind of long story short, you were in the end of your slides, you were talking about this learning parameters in MPC, and you did it on a real world platform. And I was wondering what kind of ground truth sensing you need to have in that external environment to be able to make those kind of adaptations, and what parameters specifically were being adapted.
In the example that I saw, we had a neural network, right, in which we were using to learn the dynamics. And when I talk about parameter adaptation, especially on that video with a auto rally moving in the dirt, it was actually the adaptation of the parameters of the neural network. Okay. Now, of course, you can, do things like, incorporate physics models, and then you can, like adapt these parameters and stuff like that, friction models. So that's one thing. In terms of sensors, the sensors that we had in this platform was, I think we had an IMU. Of course, we had a GPS. So these are the sensors that we use for the model adaptation, right?
Okay, yeah, thank you very much. We will close that Q&A session, and big applause for all of our speakers. Thanks for joining online. And of course, Evangelos, you don't know, but you get also a cool t-shirt for autonomous racing as all of our speakers, of course. I will hand them out later. And thank you very much for joining today.